Ideal op-amp assumptions for summing and subtracting circuits. An ideal operational amplifier is a mental model that makes hand calculations easy. Infinite open-loop gain, a sub-OL goes to infinity. The voltage difference between the plus, non-inverting, and minus inverting inputs is forced to be zero. V plus equals V minus. Infinite input resistance, no current flows into either input pin, so the inputs only see the surrounding resistors. Zero output resistance, the output can drive any load without dropping voltage. Unlimited bandwidth gain does not change with frequency, and there is no phase shift. These assumptions let us treat the op-amp as a perfect voltage copier. In real life, the gain is large, 10 to the 5 to 10 to the 6. Input resistance is mega ohms, output resistance a few ohms, and the bandwidth is limited. But for low-frequency adders and subtractors, the ideal model is accurate enough to predict the circuit behavior. Two-period inverting summing amplifier configuration with complete output voltage derivation. An inverting summing amplifier adds several input voltages while inverting the polarity. A set of input resistors R1, R2, Rn each connected to a different voltage source V1, V2, Vn. All other ends meet at the inverting node. A feedback resistor Rf runs from the output back to that same node. The non-inverting input plus is tied to ground. Derivation using ideal op-amp rules. V plus equals 0 volts ground. Because V plus equals V minus, the inverting node is a virtual ground, V minus approximately 0 volts. No current enters the op-amp input, so the only currents are those through the input resistors and the feedback resistor. By Kirchhoff's current law, KCL at the virtual ground. Open fraction V sub 1 minus 0 over R sub 1 plus V sub 2 minus 0 over R sub 2 plus V sub n minus 0 over R sub n equals open fraction 0 minus V out over Rf. Solve for V out. V out equals negative Rf times open parenthesis V sub 1 over R sub 1 plus V sub 2 over R sub 2 plus V sub n over R sub n close parenthesis. Each input is scaled by the ratio Rf over Ri and summed together. If all Ri are equal, the circuit simply produces the negative of the average multiplied by the number of inputs. V out equals negative open parenthesis Rf over R close parenthesis times open parenthesis V1 plus V2 plus Vn close parenthesis. Real-world analogy, imagine water flowing from several pipes inputs into a tank virtual ground. The tank's outlet pipe Rf carries away the combined flow, but the tank itself never fills because the outlet is perfectly sized to keep the level at 0. The pressure at the outlet, output voltage, is proportional to the sum of the incoming pressures, input voltages. 3 non-inverting summing amplifier configuration and weighted sum expression. A non-inverting summing block adds voltages without changing their sign. One common implementation uses a voltage divider on each input followed by a common summing node that feeds the non-inverting input of the op-amp. Circuit description: for each input Vi, a resistor Ri connects Vi to a summing node, and a resistor Rg ties the same node to ground. All Ri meet at the node. The node voltage V node is fed to the op-amp's non-inverting input. The op-amp is configured as a voltage follower, gain equals 1, or with a gain set by a feedback network, Rf and Rg for scaling. Derivation: gain equals 1, pure summing. 1. The node is a simple resistive network. Using the superposition principle or a linear system approach, the node voltage is a weighted average. V node equals sum from I equals 1 to n of Vi over Ri, divided by sum from I equals 1 to n of 1 over Ri plus 1 over Rg. 2. If we choose all Ri equal R and make Rg much greater than R, so the ground path is weak, the denominator is approximately n over R, giving V node is approximately 1 over n times sum from I equals 1 to n of Vi. 3. The op-amp buffers this node, so V out equals V node, or V out equals 1 plus Rf over Rg times V node if a gain stage is added. Weighted sum expression: by selecting each Ri differently, we can assign a weight Wi equal 1 over Ri relative to the others. The buffered output becomes V out equals sum of Wi times Vi divided by sum of Wi plus 1 over Rg. If Rg is made very large, the denominator reduces to sum of Wi. And Vout is approximately sum of Wi over sum of Wi times Vi. That is, a true weighted average. Analogy: think of a group of friends shouting different Vi into a microphone. Each friend stands at a different distance. Ri, the closer friend's voice, is louder, lower resistance equals higher weight. The microphone, op-amp, captures the combined loudness without flipping the sign of any voice. Explanation 4. Differential subtractor amplifier topology, gain formula and common mode rejection derivation. A differential amplifier, also called a subtractor, produces an output proportional to the difference between two input voltages, while rejecting any voltage that appears equally on both inputs, common mode voltage. Classic topology: 4 resistors form a bridge. R1 from V1 to the inverting input minus, R2 from the inverting input to output, R3 from V2 to the non-inverting input plus, and R4 from the non-inverting input to ground. Ideal op-amp analysis. Step 1. The plus input sees a voltage divider. V plus equals fraction R4 over open parenthesis R3 plus R4 close parenthesis times V2. Step 2. The minus input sees a voltage divider between V1 and Vout. V minus equals fraction R2 over open parenthesis R1 plus R2 close parenthesis times Vout plus fraction R1 over open parenthesis R1 plus R2 close parenthesis times V1. Step 3. Because V plus equals V minus, virtual short, set the two expressions equal and solve for Vout. R4 divided by open parenthesis R3 plus R4 close parenthesis times V2 equals R2 divided by open parenthesis R1 plus R2 close parenthesis times Vout plus R1 divided by open parenthesis R1 plus R2 close parenthesis times V1. Rearranged. Vout equals fraction R2 over R1 times open parenthesis R3 plus R4 close parenthesis divided by R4 close parenthesis times open parenthesis V1 minus V2 close parenthesis. Gain condition for perfect subtraction. Choose resistor ratios so that R2 divided by R1 equals R4 divided by R3 equals K. R2 divided by R1 equals R4 divided by R3 equals K. Vout equals K times open parenthesis V1 minus V2 close parenthesis, where K can be any convenient value, often 1 for unity gains. Common mode rejection, CMRR. If both inputs share a common voltage VCM, that is V1 equals VCM plus VD over 2, and V2 equals VCM minus VD over 2, the ideal differential amplifier yields Vout equals K times VD and completely cancels VCM. In a non-ideal op-amp, finite open-loop gain and resistor mismatch introduce a small term proportional to VCM. The CMRR in decibels is defined as CMRR equals 20 times log base 10 of open parenthesis differential gain divided by common mode gain close parenthesis. With perfectly matched ratios, common mode gain goes to 0, giving infinite CMRR in practice resistor tolerance. For example, 0.1% limits CMRR to about 60 to 80 decibels. Imagine two people standing on a moving walkway, the common mode motion. The differential amplifier only cares about how far apart they stand, not the speed of the walkway. If the walkway speeds up, both see the same shift, which the circuit rejects. 5. Determination of resistor ratios for specified weighted addition/subtraction, including a worked numerical example. Goal: design an inverting adder that produces Vout equals -2 V sub 1 minus 0.5 V sub 2 plus 1.5 V sub 3. Step by step. Step 1. Choose a convenient feedback resistor RF, common to all inputs. Let us pick RF equals 100 kilo ohms. Step 2. The weight for each input is minus RF over RI. Solve for each RI. For -2 V sub 1, negative RF over R sub 1 equals -2. Therefore, R sub 1 equals RF divided by 2 equals 50 kilo ohms. For -0.5 V sub 2, negative RF over R sub 2 equals -0.5. Therefore, R sub 2 equals RF divided by 0.5 equals 200 kilo ohms. For positive 1.5 V sub 3, note the sign is positive, so we need a non-inverting path. One way is to add a second op-amp configured as a non-inverting gain of plus 1.5, or we can invert twice. Simpler, use a separate non-inverting amplifier with gain 1.5, RF2 over RG2 equals 0.5. Choose RG2 equals 10 kilo ohms, RF2 equals 5 kilo ohms. Feed V3 into its plus input. Step 3. Verify. Substituting the values, the adder output becomes Vout equals negative open parenthesis 100K over 50K close parenthesis V sub 1 minus open parenthesis 100K over 200K close parenthesis V sub 2 equals negative 2 V sub 1 minus 0.5 V sub 2. The second stage adds positive 1.5 V sub 3. Resulting resistor list. RF equals 100 kilo ohms, R1 equals 50 kilo ohms, R2 equals 200 kilo ohms plus the non-inverting gain network RG2 equals 10 kilo ohms, RF2 equals 5 kilo ohms. Why the numbers matter? Selecting a moderate RF avoids loading the signal sources and keeps the op-amp's bias currents negligible. The ratios, not the absolute values, set the mathematical weights. Analogy: think of a cooking recipe where each ingredient, input voltage, is multiplied by a spice factor, weight. The kitchen scale feedback resistor stays the same, but you use different size measuring spoons, input resistors, to achieve the required amount of each spice. Explanation: 6. Application of the superposition principle to multi-input op-amp adders, step-by-step mathematical example. Concept: superposition states that in a linear circuit the total response equals the sum of the responses caused by each independent source acting alone, all other sources set to 0. Example circuit: a 3-input inverting adder with feedback resistance 120 kiloohms, resistor 130 kiloohms V1, resistor 260 kiloohms V2, resistor 3 120 kiloohms V3. All other inputs are grounded when not active. Step 1. Activate V1 only, set V2 equals 0 and V3 equals 0. Using the formula V out 1 equals minus feedback resistance over resistor 1 times V1. V out 1 equals minus 4 V1. Step 2. Activate V2 only, V1 equals 0 and V3 equals 0. V out 2 equals minus 2 V2. Step 3. Activate V3 only, V1 equals 0 and V2 equals 0. V out 3 equals minus 1 V3. Step 4. Sum the contributions. The overall output is the algebraic sum. V out equals V out 1 plus V out 2 plus V out 3 equals minus 4 V1 minus 2 V2 minus V3. Verification: plug the values into the general summing amplifier equation, and you obtain the same expression, confirming the principle. Real-world view: picture a group of kids each pulling on a rope tied to a winch, the op-amp output. One child pulls with force proportional to V1, another with V2, and so on. The winch turns proportionally to the total pull. You can imagine each child pulling one at a time, superposition, and then adding the rotations together to see the final speed. Explanation: 7. Input and output voltage range limits. Saturation, supply constraints, and headroom considerations. Supply rails: an op-amp is powered by a positive rail plus VCC and a negative rail minus VEE. The output cannot exceed these rails. It typically saturates a few hundred millivolts or a few volts for older devices below them. Example: with plus minus 15 volts supplies, a standard 741 op-amp might only swing to about plus minus 13 volts. Input common mode range: the voltage presented to either input must stay within a range that the internal transistor stacks can accommodate. For many modern rail-to-rail op-amps, the range is essentially the full supply range, 0 volts to VCC for a single supply device. Older op-amps need a margin of about 2 volts from each rail. Headroom in adder circuits: in an inverting adder, the virtual ground at the inverting node is at the same potential as the non-inverting input, often 0 volts. If the input signals are large enough such that the required output exceeds the supply limits, the op-amp saturates and the linear relationship is lost. Design tip: calculate the worst-case output magnitude using the weight formula, then compare against the available swing VCC minus headroom. If the result is larger, either reduce the gains, increase input resistors, or raise the supply voltage. Practical example: with plus minus 12 volts supplies, headroom approximately 1 volt, and a design that could produce V out equals minus 15 volts for a 5-volt input. The circuit will clip at about minus 11 volts, distorting the summed signal. Analogy: think of a car op-amp that can only drive between 2 speed limits supply rails. If you ask it to go faster than the top speed required output, it will floor the accelerator, but the speed output voltage will stay capped. leading to a speed-limited clipped response. Open-loop gain versus frequency. Real operational amplifiers have a single pole roll-off. The product of gain A and frequency F is approximately constant, called the gain bandwidth product, GBW, for a 1 MHz gain bandwidth product device. The open-loop gain is 10 to the 5th power at 10 Hz, 1000 at 100 kHz, and so on. Closed-loop bandwidth. When we close the loop with a feedback network that sets a closed-loop gain, a CL, the usable bandwidth is roughly GBW divided by a CL. In an inverting adder, a CL equals the absolute value of RF over RI for each path. If the highest magnitude gain is 10, the bandwidth becomes GBW divided by 10. Effect on summing accuracy. As frequency approaches the closed-loop bandwidth, the phase shift increases and the gain begins to fall, causing the summed output to lose amplitude and become distorted. The subtraction circuit suffers similarly. Differential gain may drop faster if the resistor ratios are not perfectly matched at high frequency. Example: a TL082 with a gain bandwidth product of approximately 3 MHz, used as a unity gain buffer where a CL equals 1, will have a -3 decibel bandwidth near 3 MHz. If the same op-amp is configured as an inverting adder with RF over R1 equal to 5, giving a gain of -5, the bandwidth reduces to about 600 kHz. Signals above that frequency will be attenuated. Design guideline: choose an op-amp whose gain bandwidth product is at least 10 times larger than the highest frequency component and the highest closed-loop gain you need. For audio, 20 kHz and gains up to 10, a 2 MHz gain bandwidth product device is sufficient. Analogy: picture a highway representing the op-amp with a speed limit representing gain. Adding more cars, meaning higher gain, reduces the effective width of the road for each car, so the maximum speed the bandwidth each can travel safely goes down. The gain bandwidth product is the product of how many cars you allow the gain and how fast the road can accommodate them, the bandwidth. Explanation 9. Typical exam type problem: design a 3-input adder with given individual gains and calculate the resulting output expression. Problem statement: design an inverting summing amplifier that provides the following weighted contributions. V1 with a gain of -3. V2 with a gain of -0.75. V3 with a gain of -2.5. Use a single feedback resistor RF and specify the 3 input resistors, then write the final output equation. Solution steps. Solution step 1: pick a convenient feedback resistor let RF equals 150 kiloohms, a standard value. Solution step 2: compute each input resistor using gain I equals -RF divided by RI. For -3: R1 equals RF divided by 3 equals 150 kiloohms divided by 3 equals 50 kiloohms. For -0.75: R2 equals RF divided by 0.75 equals 150 kiloohms divided by 0.75 equals 200 kiloohms. For -2.5: R3 equals RF divided by 2.5 equals 150 kiloohms divided by 2.5 equals 60 kiloohms. Solution step 3: draw the circuit connect V1 through 50 kiloohms, V2 through 200 kiloohms, V3 through 60 kiloohms to the inverting node. Place 150 kiloohms from output to that node ground, the non-inverting input. Solution step 4: write the output expression apply the general summing amplifier formula. Vout equals -RF times the sum of V1 over R1 plus V2 over R2 plus V3 over R3. Substituting the numbers. Vout equals -150 kiloohms times the sum of V1 over 50 kiloohms plus V2 over 200 kiloohms plus V3 over 60 kiloohms. Simplify each term. Vout equals -3 V1 minus 0.75 V2 minus 2.5 V3. Solution step 5: check headroom if the supply rails are ±12 volts. The worst-case magnitude occurs when all inputs are at their maximum, for example, +5 volts. The output would be -3 times 5 minus 0.75 times 5 minus 2.5 times 5 equals -33.75 volts, which exceeds the rails. Therefore, the designer must either reduce the gains, increase the input resistors, or limit the input amplitude to keep absolute Vout less than or equal to 11 volts. Takeaway dash the exam expects you to choose a convenient RF compute each RI from the desired gain, write the algebraic output, and comment on practical limits such as saturation. Real-world parallel dash, this is analogous to mixing audio tracks, where each track's volume knob sets a gain factor. The master mixer feedback resistor collects all tracks, each channel's potentiometer input resistor sets how loud that track becomes in the final mix.